Welcome back, everyone. In this video, we're going to finish looking at ebook Chapter 9, Lesson 3, dealing with the valence bond theory. Specifically, we're going to look at whether pi bonds contain localized or delocalized electrons and how to tell the difference between them. Let's first talk about the basic meaning of the words localized versus delocalized. This is outside of a chemistry context. So I looked at the dictionary definitions for these two words. According to the Oxford Language Dictionary, for something to be localized, that means that it accumulates in or is restricted to a specific or limited area. If something is delocalized, then it's detached or removed from a particular place or location. That's according to the Merriam-Webster Dictionary. So I found some images that can help us to kind of understand what's going on here. A house built into the ground is restricted to a specific fixed location. It's localized. A motorhome, however, is delocalized. It's removed from a particular place or location. It can travel over a variety of places. So localized is when something is in a fixed location. Delocalized is when it's not in a fixed location. It's able to be in a variety of different places. So how does this apply to molecules and electrons? Well, let's take a look at pi bonds. When we have a sigma bond, remember, is made from the overlap let's say that we have sp2 hybrid orbitals. The sigma bond is made from the overlap of those orbitals, and it exists in between the elements. These elements then are localized because they're in a fixed location. If we take electrons, we put them and make a pi bond, then the elements in that pi bond are also localized because they're in a fixed location, up above and below those elements. They're only up above or below those two elements. However, if we have resonance, then we have delocalized pi bonding. The electrons are not fixed between any two elements, but they are able to spread around across many elements. So let's take a look at the example of nitrate. Nitrate is NO3 minus. What's the electron domain geometry for nitrogen? It's trigonal planar. We know that because we have 3 electron domains. What are the hybrid orbitals around the nitrogen atom? They're sp2. Again, we have 3 electron domains, so we must have 3 equal orbitals. So we need to have 3 orbitals that are sp2 hybridized. Okay? Well, what about the oxygen atom? It looks, in this case, like we have sp2, sp3, and sp3. However, it changes between the resonance forms. Now, next. So we can't be sp2 and then sp3. It turns out that the oxygens are all sp2 hybridized. And the reason for that is because in order to have the pi bonds that exist across the molecule, those atoms must be lined up in a plane. So the whole molecule is planar. If we look at the 3-dimensional shape of the whole molecule, it is planar. And what that allows for is then the electrons that are within the resonance system to be delocalized. So because the oxygen and the nitrogens are all sp2 hybridized. They all have unhybridized atomic p orbitals, which can then overlap, form a delocalized pi system that covers the entire molecule. Therefore, the two electrons that are spread between the pi bond, and those are both above and beneath, are spread across the entire molecule. They are not localized. They are delocalized. This delocalization brings stability to the molecule. The reason for this may not be clear initially, but it's actually rather easy to understand. Stability occurs when a molecule has electrons that are lower in energy. Low energy electrons means the molecule is more stable. If you have a set of electrons that are localized in one fixed location, then they're going to repel each other at a much higher magnitude than if they're spread across an entire molecule. So simply because the electrons are able to spread out, they are lower in energy, and therefore the molecule is more stable. Delocalized pi bonding helps us to explain the stability of aromatic hydrocarbons. We'll take a look more at aromatic hydrocarbons later, but if we were to perform a reaction with a molecule with just one double bond that is localized, that means it has high energy electrons. Those electrons will react to form a bond with bromine, for example. However, if we take a look at a molecule like toluene, which has delocalized pi bonding, that means we have low energy electrons, and therefore they don't react. The pi bonds in benzene, or a molecule like it, such as toluene, we see we could have drawn them either in one configuration or the other. That's indicative that we actually have resonance, and that those electrons are spread throughout the entire molecule. So, how do you identify whether or not there'll be resonance? There are a couple patterns to look for. One is when we have a lone pair that's adjacent to a double or triple bond. What ends up happening is it's as if those electrons in the lone pair, they collapse down to form a double bond, and the electrons that were in the double bond move up onto the next atom. So it's kind of like they're shifting positions. That's how we can recognize the two different resonance forms. In practice, this could look like what we see here on the screen, where we have the extra electrons on the oxygen. They were to move down, form the double bond, and then this double bond moves its electrons onto the carbon. We can also have resonance when we have multiple double or triple bonds separated by a single bond. The electrons could be shown to move around in the following manner. And here are some examples of that. The most important one that you need to be able to recognize at this point is for something like benzene. Let's practice now. Which of the following molecules have delocalized pi bonding and which have localized pi bonding? I'd like you to pause the video and try this on your own. Come back and I'll walk you through it. Welcome back. So, in order to have localized pi bonding, we're looking for double bonds without resonance. For delocalized pi bonding, we're looking for double bonds with resonance. So, the patterns for resonance that we saw were either having a set of electrons and then an adjacent double bond, or alternating double single bonds. So in this molecule on the left, we only have localized pi bonding. While there are two sets of double bonds, they are separated by two single bonds. Therefore, they're too far away to participate in resonance. However, we can draw resonance structures for both of the other molecules. The molecule in the middle has delocalized pi bonding. That's because any way we draw the double bond, we can show those electrons as being in a different location. And therefore, they are delocalized across the entire molecule. However, for the molecule on the right, we have both delocalized and localized pi bonding. We have delocalized pi bonding here on the left because we can draw a resonance form of that part of the molecule. But on the right, these are localized. They're fixed in between the carbon atom and the oxygen atom. So let's now summarize what we've seen about covalent bonding. If you want to determine what bonds are involved, what hybrid orbitals are involved to make the bonds, you need to first draw the Lewis structure, use valence shell electron pair repulsion theory to determine the shape, then determine what hybrid orbitals are involved in bonding. You can do that by determining the electron domain geometry and the steric number. You can then use that information to determine if the molecule is polar or not by using the molecular geometry and the differences in electronegativities. To find what bonds are involved to make those bonds, we have to remember that orbitals are overlapping, and those can be either hybridized or unhybridized in the case of the hydrogen atom. That sigma bonds are formed when we have head-on overlap, that pi bonds are formed when we have side-to-side overlap, and that's only possible with p orbitals. Each single bond consists of a sigma bond, and each double bond consists of both a single sigma and a single pi bond. And that our electron domain geometries are going to determine the hybridization. If we have a tetrahedral electron domain geometry, it's sp3 hybridized. Trigonal planar is sp2, and linear is sp. That's it for this video. Thanks for watching. Have a great day.